right, part 3 of our linear programming notes, we are going to be covering how we can write inequalities from a word problem. So we'll start with this first one, bank accounts. A customer opens a checking account and a savings account at a bank. They will deposit a maximum of $600, some in the checking and some in the savings. They might not deposit all of it and keep some of the money as cash. The bank requires a minimum balance of $50 in the savings account. It does not matter how much is kept in the checking. So when we write inequalities from word problems, we're really looking at some almost kind of restrictions that we have that we need to write an equation for. So like, for example, there's a restriction here. The bank requires a minimum balance of $50 in the savings account. Now, not only do we have a savings account, but we also have a checking account as well. So we have these two different types of accounts. We want to write some equations about them. Step 1 is you want to define each of the two things that you're talking about as variables. So let's say that we're going to make checking account X and savings account Y. You could use C and S. You could make it whatever you want. I'm just going to use X and Y because that's what we're kind of used to. So for this first restriction here, the bank requires a minimum balance of $50 in the savings account. That's talking about Y, since we said savings is Y. And there has to be at least $50 in the account. So that means Y must be greater than or equal to 50. That's how much money we have to have in the savings account. Now, the checking account, it does not matter. You don't have to have any minimum balance. But if you're depositing money, we're not losing any money. So one thing that we could say is we just know that it's greater than or equal to 0, right? And I know for money, you could go into a little bit of debt, but not in this scenario because we are opening brand new accounts. So for today, as you're opening a new account, you're not going to take money out of an account that's already empty. All right, we also have another restriction. That is because we only have $600 to deposit in these two accounts. And that is total for both accounts. So what mathematical What in math means total? How do we find a total in math? That would be the sum. So we're looking for the sum of the two accounts. That would be X plus Y, and that has to be less than or equal to 600. We only have $600. Now it does say that we might choose to keep, or the customer might choose to keep some of the money as cash. So they might not put all 600 in. So it could be less than or equal to 600. And there are the inequalities for this problem. Let's try the next one. An advertising agency offers 2 packages for small businesses who need advertising services. A basic package includes only design services. A premium package includes design and promotion. The agency's goal is to sell at least 60 packages total. So far, I've already seen what my variables probably will be. That is a basic package. I'm just going to call that X. And then a premium package, I'll call that Y. And we have our first restriction, kind of, and that's that the goal is to sell at least 60 total. That means X plus Y, the total number, has to be at least 60. So that's 60 or more. So X plus Y is greater than or equal to 60. The basic advertising package has a value of $1,000 and the premium package has $1,000 of $2,500. The goal of the agency is to sell more than 60,000. So they want to sell over 60,000. Well, in this case, we need to consider not just how the number of basic packages, but the total value that they've earned when they sell that many packages. So like if you sold 2 packages, how much money would you earn? 2 basic packages. You'd get $2,000. What about 5 basic packages? That would be $5,000. What are we doing in our head mathematically? How are we figuring that out? We just take the value and multiply it by the variable, the number sold. So like 1,000 times X will tell me how much money the basic package earns, because it's $1,000 for every X sold. And then for the premium package, that's $2,500 for every premium package sold. So 2,500 times Y is the value for the premium packages. And when we want to find our total profit, we would just add them together. Now the goal is to sell more than 60,000. So this should be greater than 60,000. And it specifically says to sell more than. It doesn't say at least 60,000. So when it says just strictly more than, that's why I'm using the greater than symbol, whereas before I said greater than or equal to 60. All right, let's try the next one. Concert tickets. There's 2 kinds of tickets to an outdoor concert that were sold. Lawn tickets and seat tickets. Right now I see some variables here. So we've got lawn tickets and seat tickets. Fewer than 400 tickets in total were sold. All right, so we sold fewer than 400. That means that total X plus Y is less than 400. Lawn tickets cost $30 each and seat tickets cost $20 each. Okay. It doesn't really give us a restriction, though, about the amount of money we make. But maybe we could turn this into an equation, right? Because still, it might be nice to know how much money that we earn from the tickets that were sold. So if lawn tickets are 30 each, that would be 30X. And if seat tickets are 20 each, that would be 20Y. And this will tell us the total profit from the tickets. So even if there's not a restriction, we can still create an equation with the information we're given in the problem. Now, what do these constraints look like in context? And this is where we kind of go back to graphing that we learned in part 2. To make a quilter is buying fabric in 2 colors, light and dark. Consider the graphs that represent the 2 constraints for the quilter. So this quilter has a length constraint, which is in graph A, and a cost constraint in graph B. First question here says, explain why 2, satisfies the cost constraint, but not the length constraint. Well, the ordered pair 2, if I look on the graph, that would be right here on the first graph, and be in that same location on the second. If you notice in the first graph, this point is not in the shaded region. And as we saw when we were doing our inequalities before, the solutions were only in the shaded region. So it does not satisfy graph A here. It does not satisfy the length constraint, but for the cost constraint is within that shaded region. So it does satisfy the cost constraint. So let's see if we can find at least one pair of numbers that satisfy both constraints. So I want to look for some numbers that would satisfy both. I know that this like white triangle down at the bottom doesn't work, but what about a point like, let's see this one. This is 6, 6. Will 6, 6 work for the other graph? 6, 6. Nope, that's outside the shaded region here. Okay, so that one doesn't work. Oops. Let's try another one. Maybe 8, 2. 8, 2 right here. That's in the shaded region for length. Let's try in the other one. 8, 2. Oh, and so it's in the shaded region for both of them. So it is in both shaded regions. Take a second and see if you can find an ordered pair that works for both on your own, one that's different than the one I came up with. So let's move on to some important definitions for what we've been covering. Linear programming, it was the title of the notes, and so that you really understand what it means. We haven't actually gotten into full-on linear programming yet, but it is where we try to maximize or minimize a linear objective function. So what we do is we take a lot of constraints and restrictions, we create some inequalities, and then we look for points that are a solution to all of the inequality restrictions that we have found. Then we use that to find a maximum. So this is very helpful for things like businesses who want to maximize their profit, but might have limited resources that they can use to create their product. The objective function, this is an equation that gives quantity that is to be maximized or minimized. So the objective function, often it's a profit equation, but it can be multiple different things. That's just the most common when it comes to businesses. Then you have constraints. The constraints, these are the restrictions we were talking about before. These are the inequalities that represent the boundaries of a function. So they're going to create the lines on the graph. It's a boundary of whether we have to be greater than that value or less than that value. It's some restriction. And now this is a little bit of a new term here, and that is the feasible region. The feasible region is the region where all of the shadings overlap. I'm going to take it back real quick to part 2 when we did this. So we actually saw some feasible regions. For this problem here, this section right here, this was our feasible region because that region is where all of the shadings overlap. Or in this section, this part here was our feasible region. Again, it's where the shadings all overlap. So that is the feasible region. The feasible region can be bounded, which has a definite shape. So like thinking back to geometry, if it has some shape where there are outsides on all the sides, that's what bounded means, then there is a maximum or a minimum for that region. And that maximum or minimum actually will always occur at one of the vertices of that shape. So if you remember vertices, like for a triangle, it has 3 vertices. They are these kind of corner points here. And that's why this is actually called the corner point principle. So when we're trying to maximize or minimize our objective function, we look at those corner points.